Hello everyone, I'm Yingdi Shan, presenting our work titled Explore Data Placement Algorithm for Balanced Recovery Load Distribution. This is a joint work from Zhongguancun Laboratory and Tsinghua University. There are many distributed storage systems such as HDFS, SAF, GFS, and RAM cloud. These systems split data into smaller chunks or data units and use replication or error coding for reliability. The replicated or encoded data units are then grouped into a placement group to put into the storage system. The mapping from these data units to specific locations in the system is known as data placement. These slides provide a flow graph to illustrate the process. When new data arrives, as you can see in this flowchart, the process remains the same. The data is encoded or replicated and placed. However, this time it's within a new placement group. If a single node fails in the storage system, the lost data units on that node must be repaired and distributed to other nodes, a process known as recovery. The system repairs the lost data units across all placement groups that are correlated to the failed node. It should be noted that the recovery process of different placement groups can be parallelized. When there are many placement groups in the storage system, the recovery process can be highly parallelized, which can dramatically improve the recovery speed. Parallelized recovery has the potential to increase recovery speed so that it is limited by the cluster's bandwidth rather than the bandwidth of an individual node, improving the overall reliability of the system. However, parallelized recovery does not necessarily imply faster recovery. An imbalance in the distribution of recovery load among various nodes can lead to congestion in certain nodes and prolonged recovery times. Imbalanced recovery loads can also negatively impact the performance of certain nodes, as they may have to devote a significant amount of their bandwidth to recovery. To address this issue, a simple solution is by using fine-grained data units. By distributing a sufficient number of data units across various nodes, the recovery load can be more balanced through randomization. However, this approach to fine-grained recovery, while effective in load balancing, can increase the probability of data loss. For example, when using fine-grained data units, many combinations of simultaneous failures can cause data loss, while only specific combinations can cause data loss when using coarse-grained data units. As we delve into the problem, we can find that recovery load distribution is highly dependent on data placement. This brings us to a central question in our research. How can we design a data placement algorithm to balance recovery load? This question will guide us through the rest of our exploration. To analyze and solve this problem, we begin by characterizing the recovery load on each node in the event of a failure with the system. Let each node denote a disk or a server. Let Eij denote the load of reading data from node J when node I fails. We can then build a recovery load graph. The edge weight of the graph is calculated by summing the repair load for each placement group. Upon the arrival of new data, the system must determine an appropriate placement group to accommodate it. The objective is to minimize the imbalanced recovery load upon the addition of a new placement group to the system. The optimal recovery load distribution problem then becomes, given current data placement, how should we integrate a new placement group so that the maximal edge weight in the recovery load graph is minimized. However, the problem is hard to solve since it is an NP-hard problem. This is because the maximum independent set problem, a known NP-complete problem, can be reduced to optimal recovery load distribution problem in polynomial time. The decision form of the maximum independent set problem is to verify if a graph has a non-adjacent vertex subset of size no less than n, as shown in the figure. The detailed proof can be found in the paper. To solve this problem, we present a greedy data placement algorithm. While this algorithm may not necessarily result in the optimal recovery load distribution, it can help to balance the recovery load. This algorithm first selects the node with the smallest edge weight sum as the initial node and adds it to the current placement group. In order to achieve a uniform distribution of data, our algorithm finds nodes whose amount of data do not exceed the node with a minimum of data to a specific extent in the current storage system. Then, our algorithm will find the node with the smallest sum of recovery costs to other nodes in the current placement group and add it to the current placement group. The process is repeated until we find the data placement. Now let's shift our focus to system expansion. A vital aspect of distributed storage system is scalability, their ability to grow. The key question here is, how do we add a new node to the system? With traditional methods, system expansion often involves complex data aggregations, which can disrupt normal operations and negatively affect the system performance. Our algorithm mitigates these issues. When new nodes are introduced, data is placed onto them at a controlled speed. Over time, the system naturally achieves balance as new data is more likely to be placed on these new nodes. We carry out both macro benchmark experiments and overall performance testing to assess performance. The macro benchmark experiments performed outside of an actual storage system specifically evaluate the variability in recovery load distribution and data distribution. The figure demonstrates that greedy data placement can provide more balanced data distribution and recovery load distribution. We evaluate the effects of system expansion on recovery load distribution. Specifically, the left figure represents the scenario where an additional disk is added to the system when there are 500 placement groups stored, and the right figure illustrates the situation where two additional disks are added simultaneously. The greedy algorithm may initially create a temporal imbalance in recovery load after system expansion. The recovery load returns to a normal state as more placement groups are integrated. Simultaneous addition of multiple disks can lead to a more pronounced imbalance in the recovery load of the storage system, and it takes longer for the system to return to normal. The table demonstrates that the use of greedy data placement algorithm can significantly reduce the recovery time. Specifically, the recovery performance is found to be 1.7 to 2.4 times greater than that of the random data distribution algorithm. To summarize, we've seen that recovery load can be imbalanced in parallelized recovery. Our study demonstrates that the optimal recovery load distribution problem is, in fact, an NP-hard problem. We proposed a greedy data placement algorithm to improve the balance of recovery load. However, the field is still for further exploration. There are potentially more efficient algorithms waiting to be discovered. If you have any questions or want to discuss further, please don't hesitate to contact my email. Thank you.